Mass A is the mass of the bumper and the cart, and mass B is the weight of 3 grams. Mass A has no vertical acceleration, and the only force acting on it is the tension force. Mass B has no horizontal acceleration, and the vertical forces are gravity and tension force opposing each other. I can form a constraint where the acceleration of the cart to the left is proportional to the mass accelerating downwards. Combining the simultaneous equations of the two tension forces gives us an equation for the mass and acceleration of the cart. I have chosen sections where the cart overcomes friction and reaches its maximum acceleration. This is before the magnetic field and air resistance has enough magnitudes to decrease its acceleration, which we have ignored in the free body diagram. Using the non-constant acceleration formula from the formula sheet and integrating with the two sets of values, we get a mass of 0.277 kilograms. Using the equation for the second run, we get a mass of 0.28 kilograms. Plugging in the mass values to our acceleration formula, we'll get two theoretical accelerations of the two runs. Comparing these values to our average acceleration, we can see that the second run is more accurate. This might be because the second run has more variables, which accounts for uncertainty. Therefore, I will continue with the second mass. To find the mass of the bumper and the cart separately, I've picked a data point where the acceleration is near zero to find the magnetic force acting on the bumper. Since acceleration is near zero, we can say that the force of the cart acting on the bumper is the same as magnetic force, and the tension force on the cart is reduced by the magnetic force. The masses have the same acceleration because they're fixed to each other. We can make a simultaneous equation of the acceleration and the total combined mass. The equation shows that the cart is 0.248 kilograms and the bumper is 0.032 kilograms.
Our aim for experiment 2 was to find the dynamic friction coefficient between the water-loaded drink bottles and the surface of the skateboard. Our hypothesis is that the more weight on the skateboard, the less distance it will end up sliding, as there is a greater downwards force. Our method was we used 600ml plastic water bottles, duct taped into pairs, triplets, and quadruplets. We put the bottles on the skateboard at a line marked out by a piece of tape on the skateboard and let it roll with an initial velocity of 0 meters per second down the ramp at a distance of 1 meter. The recorded angle of the slope is 3.5 degrees. At the bottom of the slope, we had a firm metal stopper that stopped the skateboard on impact. This whole procedure is filmed by someone behind the skateboard. From here, we calculated the distance the water bottle slid down the skateboard. Variables that we had to take into consideration first was the distance. If the skateboard travels long distances, it will veer to one side, as the wheels are not perfectly round. This means we chose a short distance of 1 meter to make sure the route of the skateboard stays the same. For the bottles, we made sure the bottles of water were all filled up to the same height for everyone to ensure that the mass increments were accurate and the same. We also kept the position of the bottles on the skateboard the same to ensure the coefficient of friction is the same, as it may be different on different parts of the skateboard, considering the shoes rub on different parts more. On our first run, we loaded the skateboard with a weight of 2.4 kgs, with an average time of 2.72 seconds. The bottles moved by 2.97 centimeters. On our second run, our object had a mass of 1.8 kgs, and the average distance that the bottle traveled was 2.87 centimeters. And the average time it took the skateboard to travel that distance is 2.74 seconds. On our third and final run, we had an object of mass 1.2 kgs. During this final run, the bottles traveled an average distance of 3.2 centimeters, and it took an average of 2.63 seconds for the skateboard to travel the 1 meter. For our calculation, we used kinematics and our values of time and displacement to compute for the velocity and acceleration of the skateboard on each run. When we have computed for those numbers, we are able to use F equals ma to calculate the coefficient of friction.
Using kinematics and entering the final values of time and displacement, I can find the acceleration of the skateboard down the slope and the final velocity of the skateboard. Using the final velocity of the skateboard and the bottle displacement, I can find the deceleration of the bottles. Drawing a free body diagram and using the rotated coordinate system, I can find the supporting force and the friction force using the deceleration calculated earlier. Friction equals mu n, therefore the coefficient of dynamic friction is 0.99. For the other two attempts, the coefficient of dynamic friction is consistent. Therefore, I conclude that the coefficient of dynamic friction between a skateboard and a bottle is 0.99.